Continuing through the periodic table, let's look at column 5A. Nitrogen, the phosphorus, arsenic, antimony, bismuth. In this case, we're seeing more of our elements at the top remain far more covalent. Nitrogen and phosphorus both readily make large numbers of covalent bonds. We saw silicon made some, but it was much closer to just being an ionic silicon-oxygen compound. It could chain a little bit, and so it was more of a molecular solid than truly ionic. Phosphorus, on the other hand, can just make readily covalent compounds in the plenty. You can have phosphorus trichloride, phosphorus pentachloride. You can make phosphates if you push it, but even that's a covalent polyatomic. The phosphorus still has covalent bonds. It's not really building up a charge on itself. Nitrogen readily makes covalent bonds. In fact, nitrogen has the curious behavior of being one of the only components to be basic in organic molecules. When you have various carbon compounds with a nitrogen and some hydrogens, there's a lone pair available on nitrogen, and it is quite able to pick up an H+. When this happens, you end up with a nitrogen that uses its lone pair to create the bond to that hydrogen and still has bonds to the rest. But this results in a formal charge of +1 on the nitrogen. The charge that used to be on the proton is now on the nitrogen as its electrons are stretched further out to occupy the orbital around that hydrogen. This makes it a base. It's able to acquire H+. Compared to other elements that generally have lone pairs left on them, like oxygen or sulfur or fluorine or chlorine, they're not prone to picking up an H+ and becoming positive nearly as easy as nitrogen is. More often, they tend to give away an H+ and become negative. And so oxygens and sulfurs will be more acidic, where nitrogens will be more basic. As a result, a lot of the compounds that interact with neurotransmitters often will have a nitrogen involved. The receptor site has some negative components, and positively charged molecules tend to fit into it nicely. So many prescription painkillers and many drugs, amphetamines and morphine and the like, have nitrogen in their structure. Nitrogen is also wildly abundant. N2 is its normal form on Earth. It is a dimer gas, and it occupies most of the atmosphere. Around 79% of Earth's atmosphere is dinitrogen, because it's not particularly reactive. It's very hard to break that triple bond. It's very stable, and so this does not tend to react with other things easily. Converting it into ammonias and nitrates and so on is one of the marvels of the modern industrial age. If we weren't able to do that, we wouldn't have enough fertilizer. Plants naturally do this, usually in conjunction with bacteria that have specialized an enzyme to deal with this, to turn it into ammonia. We are still studying that to figure out how the heck life goes about doing it. Because at present, we need very high pressures and heats and good catalysts in order to make ammonia. Unlike carbon, which could chain infinitely together and in various patterns and shapes, nitrogen will link together, but it's not particularly stable. If you have nitrogens, you can link several nitrogens around. And you can even get these to bond off to other things, and so on and so on and so on. However, these tend to reorganize their bonds. You'll swing one over here, you'll swing one over there, and what you'll get instead is a bunch of triple bonded nitrogen. This is significantly more stable. You have a bunch of individual dimers. You also have a bunch of gas. A lot of explosives are built around nitrogen bonds. Some of the most explosive materials ever made are just nitrogen linked in odd patterns. It will connect, but it's not particularly stable, especially at higher temperatures. Unlike carbon, which is remarkably stable as it links into these larger structures. Phosphorus actually will make more molecular solids. Normally our phosphorus is found in a tetrahedral pattern. where 4 phosphorus make a 4-pointed, imagine a 4-sided dice. This is standard white phosphorus. Purified phosphorus is relatively dangerous. It tends to react with things. It's not too hard to spontaneously combust it. And so these generally have to be stored under some protective material. However, if you can remove the atmosphere and heat this up, some of these bonds will break and they'll react with another neighboring one. This will relieve some of the stress, folding these up and allowing them to expand to interact with each other. As a result, you'll end up making a more chained system with triangles of phosphorus linked together. This is red phosphorus. These will make sheets. Because they're one large molecule, they're sort of a plastic. These are not readily soluble, and they're actually a bit more stable to spontaneous combustion and the like. Normally, a match is made out of a lot of red phosphorus, and when you strike it and grind against it, you can break some of this off as white phosphorus. You'll put enough heat in, break a bond, reconnect, and there's a significant heat from the striking to cause that white phosphorus to then spontaneously combust, heating up your perchlorates on your match and making even more fire. So red phosphorus is reasonably stable. We can use it for things like matches and so on. There are other forms of phosphorus as well, but they tend to be even more difficult to isolate and store. In general, P4 is how we think of the molecular component of phosphorus, little tetrahedral P4s. Arsenic and antimony are fairly toxic materials. Arsenic is a historic assassination element. Get a little bit into somebody's tea, and it would slowly poison them as you gave it to them over time. Antimony, not as good as a assassination tool from the ancient days. However, it's still a fairly toxic metal. Both of them are a little bit metalloid. They will make somewhat covalent seeming bonds in certain cases, but they also make just large sheets of interconnected atoms. They're not fully metallic and they're not fully covalent. Bismuth, however, is rather peculiar in this respect because it is the lowest toxicity of any heavy metal. So much so that Pepto-Bismol uses bismuth. It actually has a settling effect on our stomach when combined with certain things. It's got kind of a pink color to it. Bismuth is being used to replace certain things like lead weights or lead shot in certain places because it's just considered to be less dangerous. It also makes beautiful square stair-step crystals that get a rainbow sheen on them. If you ever had a chance to see a solid bismuth crystal, or make one, they're very pretty. It is definitely a metal. It acts very much like a metal, but is a surprisingly non-toxic metal compared to other heavy metals. Continue our trends. The 6A. Oxygen, sulfur, selenium, tellurium, polonium. Here again we see as our columns move farther to the right, we get more and more elements that tend to be somewhat covalent. Oxygen, sulfur are extremely covalent. They will readily make covalent bonds all over to any other non-metal. Selenium is a little bit of metalloid. It will make some covalent compounds. And in fact, carbon compounds with OH or carbon compounds with SH or carbon compounds with SEH are all known. Alcohols, thiols, selenols. Well, alcohols are used all over in chemistry. Thiols do show up, but these tend to be very odorous because they somewhat match how oxygen would interact in ways that our biology expects, but not to the same degree. They cause problems. Thiols can be rather dangerous. H2S is effectively the rotten egg smell. It's what you actually smell if you smell a fart or an egg, rotten egg or something. Hydrogen sulfide is a lot like water, but the atom in the center is different, the electronegativities are different, the bond angles are different. They have a similar formula, but they're different enough that when it goes to interact with something water does, it doesn't interact quite the same. But it can tend to get to the same places. This just causes problems, and it can interact with things that are also sulfur in other places and make disulfides. Curiously, we have a defense mechanism for this. It smells terrible. We recognize the smell, we try to avoid it, and as long as you can still smell it, you're fine. It hasn't done enough to you to really matter. But if you get too high of a level of hydrogen sulfide, it starts interfering with various enzymes and processes in the body, and about the time that starts to happen, it disrupts your sense of smell. So curiously enough, if you ever work with it in lab, as long as it smells like farts, you're fine. The moment it starts smelling okay, you have to go outside and get fresh air, because you have to wait for it to leave your body to bring down the concentration to a not dangerous level. Well, this continues. SEH is just as bad. So if you have H2SE or any selenols, they smell 1,000 times worse. So much so that there's reports where a lab spilt a small container in the lab, and the town for a kilometer in any direction was calling the police about the odor, to the point they thought there was a dangerous chemical spill simply because it is so unbelievably foul smelling. Given the prevalence of OH, especially from water, that life contains, these similar compounds in the same column can have somewhat similar interactions, but not similar enough for us to ignore them. They end up causing problems. Oxygen on Earth actually has two major forms: dioxygen that we breathe and ozone, O3. This can be created when lightning strikes and the like hit oxygen in the atmosphere. You can break a few molecules apart and reorganize them. This is a bit more reactive, and so it tends to break down over time. It's also good at absorbing ultraviolet light, because its electron distribution is different than for O2. And so the ozone layer helps protect the Earth from the deep ultraviolet light that comes from our sun. It's also an example of a situation where we've already shown human activity can completely alter our atmosphere, with the hole in the ozone layer that formed due to CFCs that we released, refrigerants that we mostly don't use anymore. But that's because we recognize the danger. If we were going to lose the ozone layer, we were suddenly going to get bombarded by a lot more high-energy radiation. Protecting the ozone layer required us to form treaties around the world that stopped the use of various chemicals that catalytically destroyed it. And so we cut back and nearly eliminated chlorofluorocarbons. There's still scattered use, but significantly less. Over the last 30 years, we've seen the ozone stop shrinking and start to expand and fill the hole back in. So we know that we both can alter the atmosphere and can change things to fix it. We just need to do that for our other problem molecules like CO2. Sulfur has a variety of forms. Its most common is S8. It makes a ring of 8 sulfur atoms. If you heat this up, the rings will break and they'll link together, and you can get this large chains of sulfur in various sizes. But as it cools, it will tend to break back into ring systems. So while sulfur can have many reasonably stable forms, its most stable, most common is the S8. And finally, let's talk about 7A. Halogens, the halides, our fluorine, our chlorine, our bromine, our iodine. This column tends to make ions that are -1 unless they're covalently bonded. And they all make dimers. You can have F2, Cl2, Br2, I2. Curiously, we're a gas for the first two, but we're a liquid for bromine, and we're a solid for iodine. As we go down the periodic table, we make these molecules. When they're paired to themselves in their pure form, well, they're non-polar. The electrons are evenly spread over both atoms, but the atoms get bigger. As we get to chlorine, they just have a larger surface. As we then get to things like bromine, All the atoms, again, are bigger. Their size gets larger, which gives them more of a surface to interact with, more of a chance for the non-polar forces that can occur between molecules to occur. And so while fluorine and chlorine are still small enough and light enough that those forces at room temp are not sufficient to keep the liquid, they break apart and become gas. For bromine, it's big enough and heavy enough, it has enough of those interactions that it is a liquid at room temp. And iodine is a solid. Curiously, it doesn't take a lot of energy to break iodine into the gas phase. It sublimes quite readily. And so a jar of I2 actually has a vapor pressure of I2 bouncing around inside it, and so crystals will grow and break constantly inside a container of iodine. One other thing that can happen for the chlorine, the bromine, and the iodine is they're pretty good at making a series of oxo acids. You can have an acid of hydrogen chloride, but you can also have HClO, hypochlorous acid. You can have HClO2, chlorous acid, HClO3, chloric acid, and HClO4, perchloric acid. As more and more oxygens get added to the halide, it becomes more and more acidic. It is easier to give away that H+. This makes various earlier versions prone to oxidation. Hypochlorous acid, when replaced with an Na, sodium hypochlorite, this is bleach. This tends to react with other things and oxidize them. It either can be oxidized from some chemicals that add more oxygens, or it can give away its oxygen to attach to something else. So these halides have a variety of uses, not only as acids, but also oxidants in various forms, to either oxidize something further or to reduce something by becoming more oxidized. You can do this with the bromine and iodine as well. You can't, however, do it with fluorine, as you have to break the octet to get to these higher oxidation states, and fluorine cannot do that. Second row elements cannot break their octet. And finally, we have the 8A, the noble gases. Noble gases are characterized by atomic behavior. They are just individual atoms floating around. They don't bond with other things. They're not dimers. They're not S8 or something like that. They don't make infinite chains. They float around as individual molecules. It is possible to cool them enough to make them liquid. They do have a surface that can be temporarily polarized from impacts and induced polarization, but they are largely a non-polar electron cloud that has very little interaction. So these are gases at room temp and only liquid if you get very cold. Well, you can get things like argon to liquefy at liquid nitrogen temperatures. Helium you have to get down to near absolute zero. Liquid helium is used in the coldest necessary temperatures for a lot of equipment. Things like MRI devices need liquid helium surrounding the magnet to keep the magnet cold enough to do the superconducting. And so the process to cool the helium down significantly to make it liquefy is rather energy intensive, but eventually you can cool it down enough to make it liquid and then use that to keep superconducting equipment cold. It'll slowly boil off over time, taking the heat away with it, since its boiling point is down near 0 Kelvin. And so this keeps our magnets very cold. This tends to be why a lot of our satellites with advanced instruments also eventually die. Usually we need the advanced instrument to be kept very cold. Electrical noise messes up the signals. Most of our detectors use an electrical current to determine when a photon has hit the plate. However, if there's some thermal heat, then your electrons are randomly moving anyways. This will look like current, or at least noise, and makes it hard to see really tiny amounts of light from very distant galaxies. And so we tend to cool our equipment down with liquid helium, but eventually that runs out in space and the equipment dies. While generally the noble gases are considered non-reactive, there are a few exceptions. For a long time we thought they were unreactive, but it was discovered that with the right compounds, you can get xenon to react and make fluorinated compounds, and even a few oxygen-containing compounds. Xenon difluoride, xenon tetrafluoride, xenon hexafluoride are well enough prepared. In fact, a few of them are used industrially because they tend to be very good at dissolving silicon rubber. And so you can dissolve away a silicon rubber mold from something without having to actually pull and peel it apart. A few compounds of krypton have also been discovered. However, we have not yet been able to make any from neon or helium. They are simply too stable and unreactive. So here we reviewed a few additional insights into the behavior of different columns of the periodic table, beyond simply that things tend to be larger at the bottom, smaller at the top, or larger on the left, smaller on the right. Within a column, there can be a variety of differences. While our metal columns tend to be metals the entire time, over here in the nonmetals, we see a changing progression as we follow along this line of metalloids. If you're slightly above it, you tend to be a little bit more covalent, but still have some metallic character. If you're below it, you tended to be far more metallic, but have a little bit of covalent character. So these materials don't quite behave one way or the other, which leads to interesting uses like silicon for electronics. It's very useful for us that silicon isn't quite a metal, but still lets electrons get conducted if you put a little force into it, so it becomes a semiconductor. Aluminum tends to be something we think of as ionic, but we also can make it be covalent. You can have it interact with hydrogens fairly well. They'll actually make hydrides, H minuses, when they transfer, but it has a covalent bond between aluminum and the hydrogen at the time. Arsenic, germanium, tellurium, antimony, these all have a variety of industrial purposes because of their odd behavior of not quite being covalent or ionic. And then the nonmetals react to form covalent bonds. These will share electrons. They'll come in a variety of forms. Some of them only want to stick to one or two things. Others, like carbon, can have infinite series of carbons with other things attached to it, leading to the complexity of life, where carbon with other things bonding only once or twice to it make up the variety of organic molecules. So nitrogen, oxygen, phosphorus, sulfur, and a few halides on carbon allows carbon to incorporate those other atoms to create neat structures, where those other atoms only need to bond the carbon once or twice.